What is fault mirror in geology? In geology, a fault mirror refers to a smooth, polished surface that forms along a fault plane due to the movement of rocks against each other. Faults are fractures in the Earth's crust where blocks of rocks have moved relative to each other. These movements occur primarily due to tectonic forces, such as the shifting of tectonic plates or the release of accumulated stress within the Earth's crust. When rocks on either side of a fault move past each other, they can grind against one another, causing abrasion and creating a smooth, mirror-like surface along the fault plane. This polished surface is known as a fault mirror. Fault mirrors are often observed in areas where the movement along the fault has been significant and ongoing. The formation of fault mirrors is an important indicator of past tectonic activity. Geologists study fault mirrors to understand the history of fault movement, including the direction and magnitude of past displacements. By examining the characteristics of fault mirrors, such as their orientation, striations, and degree of polish, geologists can reconstruct the sequence of events that led to the formation of a particular fault and gain insights into the tectonic processes that have shaped the Earth's crust over time. Fault mirrors can vary in size and scale, ranging from microscopic features observed under a microscope to large, exposed surfaces that are visible in outcrops and cliffs. In some cases, fault mirrors may be associated with other structures, such as slickensides, which are linear grooves or striations on the fault surface caused by the movement of rocks past each other. Overall, fault mirrors are valuable geological features that provide important clues about the dynamic processes that have shaped the Earth's crust and contribute to our understanding of plate tectonics, seismic activity, and the formation of geological structures. Importance of fault mirror in geology. Fault mirrors play a crucial role in the field of geology, offering valuable insights into various aspects of the Earth's dynamic processes and the formation of geological structures. Here are some of the key importance of fault mirrors in geology. Tectonic activity reconstruction. Fault mirrors provide essential information for reconstructing past tectonic activities. By analyzing the orientation, displacement, and characteristics of fault mirrors, geologists can deduce the history of movement along the fault. This helps in understanding the timing, direction, and magnitude of tectonic events, contributing to the broader understanding of plate tectonics and the geological evolution of a region. Seismic hazard assessment. Fault mirrors aid in assessing seismic hazards by providing evidence of past earthquake activity. Through detailed analysis of fault mirrors, geologists can determine the frequency and magnitude of past earthquakes along a fault. This information is crucial for evaluating the seismic risk in a particular area and developing strategies for earthquake mitigation and preparedness. Structural geology studies. Fault mirrors serve as key features for structural geologists studying the deformation of rocks and the formation of geological structures. By examining fault mirrors along with other structural features such as folds, joints, and foliations, geologists can unravel the complex history of rock deformation and understand the mechanisms responsible for the formation of mountains, basins, and other geological features. Paleoseismology. Fault mirrors provide valuable data for paleoseismologists studying the history of earthquakes and seismic activity. By analyzing fault mirrors along with associated sedimentary deposits and other geological evidence, paleoseismologists can reconstruct the timing and magnitude of prehistoric earthquakes. This information helps in assessing the long-term seismic behavior of fault systems and understanding their potential impact on society and the environment. Resource exploration. Fault mirrors can also be significant indicators for resource exploration, particularly in the search for hydrocarbons and minerals. Faults can serve as pathways for the migration of fluids, such as oil and gas, and the deposition of mineral deposits. Understanding the characteristics and movements along faults, as revealed by fault mirrors, can help in targeting exploration efforts and identifying potential reservoirs or mineralized zones. Engineering applications. In engineering geology, the study of fault mirrors is essential for assessing the stability of structures and infrastructure in regions prone to tectonic activity. By understanding the nature and behavior of faults through the analysis of fault mirrors, engineers can design buildings, bridges, dams, and other critical infrastructure to withstand potential seismic hazards and minimize the risk of damage or failure. In summary, fault mirrors provide valuable information for understanding the Earth's tectonic processes, assessing seismic hazards, studying structural geology, conducting paleoseismological investigations, guiding resource exploration, and informing engineering practices. Their significance extends across various fields of geology and earth sciences, contributing to our broader understanding of the dynamic processes that shape the Earth's crust and influence human activities and the environment. How to find fault mirror in field. Finding fault mirrors in the field requires careful observation and examination of rock outcrops or exposures where faults are present. Here's a detailed guide on how to find fault mirrors in the field. Locate fault zones. Begin by identifying areas where faults are expected to occur based on geological maps, satellite imagery, or topographic features. Faults are often associated with linear features such as cliffs, escarpments, or valleys. Look for areas where rocks appear to be offset or displaced along a linear trend. Inspect rock outcrops. Once you've located a potential fault zone, examine nearby rock outcrops or exposures where the fault is visible. Look for areas where the rock surface is exposed and accessible for close inspection. Search for smooth surfaces. Scan the rock surfaces for smooth, polished areas that may indicate the presence of fault mirrors. Fault mirrors are typically characterized by their reflective, mirror-like appearance, often appearing as shiny or glassy surfaces. Check for lineations. Inspect the smooth surfaces for linear features or striations that may be present. Fault mirrors often exhibit striations or grooves, known as slickensides, which are caused by the movement of rocks against each other along the fault plane. Slickensides may appear as fine scratches or grooves oriented parallel to the direction of fault movement. Observe orientation. Note the orientation of the fault mirrors relative to the direction of fault movement. Fault mirrors may exhibit distinctive orientations or alignments corresponding to the direction of fault displacement. Use a compass or geological compass to measure the orientation of fault mirrors accurately. Look for offset features. Examine the adjacent rock layers or formations on either side of the fault for evidence of displacement or offset. Fault mirrors are often associated with offset features such as changes in rock type, thickness, or bedding orientation. Document findings. Take detailed notes and photographs of the fault mirrors, including their location, orientation, size, and any associated features. Record observations of any slickensides, lineations, or other distinctive characteristics observed on the fault surface. Consider geological context. Evaluate the geological context of the fault zone, including the types of rocks involved, the nature of the faulting, e.g., normal, reverse, strike-slip, and the structural features observed in the surrounding area. This information can help in interpreting the tectonic history and kinematics of the fault system. Repeat observations. Repeat the process of searching for fault mirrors along different sections of the fault zone to gain a comprehensive understanding of their distribution and characteristics. Compare observations from multiple locations to identify patterns and variations in fault mirror development. Exercise caution. When examining fault zones in the field, exercise caution and be mindful of potential safety hazards, such as unstable rock formations, steep terrain, or hazardous weather conditions. Take appropriate safety precautions and avoid placing yourself in dangerous situations while conducting fieldwork. By following these steps and employing careful observation techniques, geologists can effectively locate and identify fault mirrors in the field, contributing to our understanding of fault dynamics, tectonic processes, and geological structures.